concept of logarithmic functions and exponential functions, but now we're going to use the identity or the property, the one-to-one property to solve the equation of exponential equations and logarithmic equations. All right. So the setup is that for this lecture, I'm going to focus. The first half of the lecture is solving exponential equations. The second half is solving logarithmic equations. When solving a logarithmic equation, it's a little bit more involved because remember, when you study logarithmic functions, you need to care about the domain of the functions. So let's focus on exponential equation first. All right, so the setup is again that you need to impose certain conditions that the base are constant and they have to be greater than 0 and different from 1. All right. So now if you have the equations of the form that a to the x equal to a to the y, right, you kind of, what I'm about to say again is not mathematically correct, but it's easy for us to understand the problem. The base cancel out, all right? Or basically you just set the exponents equal to one another, all right? If you have the same base here, a to the x equal to a to the y, then the exponent is going to be equal to one another. You with me on that? So that's the one-to-one property that we're going to use to solve exponential equations. Okay. Another way to look at this step, right? Going from this equation, a to the x equal to a to the y, to x equal to y, what you technically do is that you take ln, you take log of base a on both sides of the equations. Okay, so bear with me here. Technically, what you're going to do is you have a to the x equal to a to the y, and then you take log of base a of a to the x equal to log of base a of a to the y. Technically, this is mathematically correct approach, right? So you take a log of base a on both sides of this equation, a to the x equal to a to the y, and then you apply the cancellation property between a logarithmic function and exponential function. Now, if you go back to the previous lecture, you have property 3 and 4. Those are the cancellation properties. Okay. So log of base a and exponential function cancel out. You're left with x on the left-hand side. Log of base a and exponential functions cancel out. We have y on the right-hand side. So this should give you x equal to y. And that is how you went from the first equations to the last equation. Okay. This is technically correct. That you see. But after a while, when you're doing the problem, you get familiar with the approach, with the procedure, you may just skip all the steps and go directly from this equation, a to the x equal to a to the y, to x equal to y. You with me on that? Okay. So with that in mind, let's start with example 1 here. So the first equations you have is e to the negative x squared equal to e to the negative 3x minus 4. As you can see, the base are the same. So you just set the exponent equal to one another. So hopefully that's straightforward enough for us. So here you have negative x squared equal to negative 3x minus 4. Now just move everything onto one side of the equations and you get 0 equal to x squared minus 3x minus 4. So basically at this point, you're solving the quadratic equation and no longer an exponential equation. So I moved the negative x squared to the right-hand side because I want to avoid dealing with negative in front of x squared. Okay. So you have on the right-hand side a quadratic expressions. You can factor it, or you can use quadratic formula to solve for the solutions. Whatever means that you feel comfortable with, use it. Okay. So on the right-hand side, you have x minus 4 times x plus 1. So therefore, you have solution x equal to -1 or x equal to 4. So those are the solutions of the equations. Any questions so far? All right, now number 2. Right. So what do you do? So number 1 is easy. You see that the bases on both sides are the same. So you just match the exponents together. Simple enough. But now for number 2, as you can see, the bases are different. But you can manipulate the bases so that you can arrive at the same base. All right. So 9 has something related to 3, and 27 has something related to 3 as well. So 9 is 3 squared, 27 is 3 cubed. Right. You can rewrite those numbers as that. So here 9 is 3 squared power x, and 27 is 3 cubed. Okay. Now for the left-hand side, 3 squared raised to the power x, you can rewrite this as 3 to the power 2x. And on the right-hand side is 3 cubed. Now you have the same base, you just match the exponents together, and you get 2x equal to 3, or x is equal to 3/2. Any questions? Good. All right, number 3. Again, the bases on both sides are different, but again, you can manipulate the bases to arrive at the same one. So 2, just leave it like that, but 4 has something related to 2, right? So 4 is 2 squared. So we write 4. You have 2 to the power x minus 1 equal to 2 squared to the power x plus 3. Or the right-hand side can be written as 2 to the power 2 times x plus 3. So the base is the same now. Just match the exponents together. You have x minus 1 equal to 2 times x plus 3. And then you solve for x from here. So this is a quick, easy solve. So you have x minus 1 equal to 2x plus 6. Now combine everything related to x together. So you have x minus 2x equal to 1 plus 6, or negative x equal to 7, or x is equal to negative 7. You good? Any questions? All right. So can you try number 4 and number 6? I will do number 5 later. So for now, take a little bit of time and try to do number 4 and number 6. Very similar approach as we did in problem 2 and 3. So let me do number 4. All right, so number 4 here is that, again, the bases are different, but you can turn the 1/2 into something related to 2. Right. So you can rewrite 1/2 as 2 to the negative 1. You with me on that? Again, remember the phrase, when you cross the line, you change the sign, right? So 1/2 to the first power, you can rewrite that as 2 to the negative 1, and then raised to the power x minus 4. Okay. Now the left-hand side remains the same. You rewrite the right-hand side as 2 to the power negative x minus 4. So the bases are the same now. You just match the exponents together. So you get x squared minus 4x equal to negative of x minus 4. And then you distribute the negative to the parentheses. And you get x squared minus 4x equal to negative x plus 4. And move everything to one side of the equation. And you get x squared minus 3x minus 4 equal to 0. So that is very similar to what we did in the first equations. So the solutions here is x equal to negative 1 or x equal to 4. All right. Any questions? This look like a lot of you did well on number 6, but not so much on number 4 because of the 1/2. So you change that again. Remember, change that to 2 to the power negative 1. All right, so let me cover number 5 as well. So look at the equation and you see that on the left-hand side is base E, on the right-hand side is base 1. How would you turn 1 into E? Right, because you want to make both sides of the equation have the same basis. How would 1 relate back to E? What power should I raise E to get 1? 0. Okay. So you can rewrite the right-hand side as e to the 0. Okay. Now you just match the exponents together. You get x squared plus 5x plus 6 equal to 0. Again, here you can factor or you can use quadratic formula to solve the solutions. You have x plus 5, sorry. X plus 2 times x plus 3 equal to 0. So the solution x equal to negative 2 or x equal to negative 3. Now number 6. Okay. Am I moving too fast? Good pace. So number 6, you rewrite 9 as 3 squared. You get 3 to the x to the third power. Sorry, 3 to the x plus 3 equal to 3 squared to the power 2x minus 5. The right-hand side is equal to 3 to the power 2 times 2x minus 5. You have the same base. You match the exponents together. X plus 3 equal to 2 times 2x minus 5. Or x plus 3 equal to 4x minus 10. Now you solve for x, right? So you have negative 3x equal to negative 13, or x is equal to 13 over 3. Cool. Any questions? Good. All right. So the first page is easy, solving exponential functions where the bases are the same. Right. Those are easy. Okay. Now we move on to the second page of the selection notes, and you will see that on both sides of the equations, you have different bases, and there is no way you can manipulate bases so they can arrive at the same base at all. Okay, so 2 to the x equal to 5. There's no way you can manipulate 2 so that is match 5, or you manipulate 5 and match 2 at all. Okay, so now what you do is you go back to the very beginning and you apply this technique. You take a log on both sides of the equations. You with me on that? All right. When you do that, you have, let's say, power x. You can bring it down to become multiplications using the power property. Okay, so let me demonstrate that. Here you have 2 to the power x equal to 5. Okay. Now you want to solve for x, or you basically want to bring x down to become multiplications. Something x multiplied with something. All right. Now what you do is that you take a log of base 2 on both sides of the equation. Wait. All right, so let's do that first step. I'm gonna do log of base 2 of 2 to the x on both sides of the equation. Why log of base 2? Because the exponential function carrying the x is a base 2. So that's why I choose a log of base 2 to do it. Okay. Now on the left-hand side, I have log of base 2, and then the exponential function of base 2. So this two cancel out, and I'm left with just x. Okay, so that's one way to think about it. Another way to think about it, set up for the next approach that I'm going to do in a different problem, but is that I can rewrite the left-hand side as multiplication. Okay, so I can bring down the power x here. It's become x times log of base 2 of 2. The right-hand side remains the same. Okay. And log of base 2 of 2 is equal to 1. All right. Again, you ask yourself questions, what power should I raise this 2 to get 2? And the answer is 1. Okay. So therefore, the left-hand side becomes x only. And the right-hand side log of base 2 of 5. And now you have to leave it like this. Without a calculator, we don't know what that is. Okay. Cool. All right. So that's one approach. That you look at the base of the exponential functions and you use or you apply the log of that same base on both sides of the equations to bring down the x. Yep. Now, another approach is that you can just technically apply to all of the problems that you take ln on both sides of the equation, regardless of the bases that you see. Cool? Because it's convenient to use ln. It's easy to memorize. It's easy to use a calculator on. Okay, so that's another approach that you can use. Right. Here, For second problem, you have the equation of 3 to the power x equal to 14. Two approaches that you can use. The first one is you can take log of base 3 on both sides of the equations. That's the approach that we did in the first problem. Another approach here, now we're going to do is take ln on both sides of the equation. Ln stands for natural log function. Okay. So that's what I'm going to do. I take ln on both sides of the equation. No matter what the basis that you see in the exponential equation, just apply ln on both sides of the equation. Then for the next step, I bring down the power x by using power property. And I got x times ln of 3 equal to ln of 14. And then to get x by itself, you divide it both sides for ln of 3. And you get x equal to ln of 14 divided by ln of 3. Convenient. It's very convenient. I don't know exactly the value of ln of 14. I don't know the exact value of ln of 3, but it's a lot similar to enter this in a calculator than entering log of base 2 of 5. Okay. You don't know the special formula, and it's really hard to enter that log of base 2 of 5 in the calculator. All right, so again, you have two approaches that you can use, but it's very convenient to just apply natural log of both sides of the equation, regardless of the basis you see. Now, number 3, I'm going to apply ln on both sides of the equations. As you can see of this equation, there are two different bases. One is base e and the other one is base 7. Okay, there's no way you can manipulate one or the other. So what I'm going to do is apply ln on both sides of the equations. And on the left-hand side, I can rewrite this as x times ln of e equal to ln of 7. Now, what is ln of e equal to? ln of 5 is 2.57, but ln of e is not 1, right? Because ln is log of base e. Right? So log of base e of e is 1. You with me on that? So ln of e is always equal to 1. So here you have this is equal to 1. Therefore, the equation becomes x equal to ln of 7. Did you give me the, Lalandra, did you give me the answer earlier? Like the final answer? Oh, okay. So it's ln of 7, 2.5 or something like that? Can someone try it? It's 1.95. Never mind. 1.95. So x equal to ln of 7. Just leave the answer like this because you are not allowed to use the calculator in the test quiz. Just leave the answer. Know exactly what that is. All right, next equations, e to the x plus 3 equal to 2 to the x. Again, apply ln on both sides of the equations. Yeah. Left hand side, I get x plus 3 times ln of e. And on the right hand side, I can rewrite this as x times ln of 2. And ln of e is equal to 1. The left hand side becomes x plus 3. And the right hand side is x times ln of 2. ln of 2 is 0.693, like that. But now just group everything related to x on one side of the equations. So the equation becomes x minus x times ln of 2 equal to -3. Then x on the left hand side, x is the common factor. You're left with 1 minus ln of 2 equal to -3. And when you solve for x, you get -3 divided by 1 minus ln of 2. All right, so you solve and you get the equation of the solution x equals this number, whatever. What's the point of doing this? This is pointless, right? Right? Have you ever wondered? Right? Not because like, say so. All right. So in reality, again, you don't have the luxury of having function. This is convenient for us to learn the method, to learn the approach. But in reality, you have a bunch of data. We collect data about each data. On, right? And you usually use these functions to fit the data onto, right? And then some data set uses this function e to the x plus 3. Some data set will use the function 2 to the x. And these two curves will eventually maybe intersect to one another. And when they are intersect at one point, they are equal. And by solving this equation, you arrive at that x location of the points. Okay, so it means something in a way. It means something. Okay, but in reality, that's actually how it works out. Where you have one set of data, you have another set of data. You fit two curves. The two curves intersect at one point. Okay, or multiple points if you quadratic functions. Do you get the idea of why, in a way, that we try to learn how to solve this? Okay, good. Now, number 5, you have 3 to the power 1 minus 2x equal to 4 to the x. Again, just take ln on both sides of the equations. And then you can rewrite this as 1 minus 2x times ln of 3 equal to x times ln of 4. So this problem is a little bit more involved. Now, again, the idea is to solve for x. Okay. So the next step is to distribute ln of 3 into the parentheses. You get ln of 3 minus 2 times x times ln of 3 equal to x times ln of 4. And then you group everything related to x on one side of the equations. You should get negative 2x times ln of 3 minus x times ln of 4 equal to negative ln of 3. And now all the term in the equation carries a negative sign, so I'm gonna cancel all of them out. I don't want to deal with the negative number. So I have 2x times ln of 3 plus x times ln of 4 equal to ln of 3. And then on the left-hand side, I have x as a common factor. And I left with 2 times ln of 3 plus ln of 4 equal to ln of 3. To solve to get x by itself and divide both sides for this number. Even though it looks complicated, but remember, if you have a calculator, this number becomes very simple. Okay. So divide both sides for this number, and I will get x. So I'm very surprised that some of you use the first approach. That's awesome. That's awesome. All right. But let me quickly do this problem. So I usually just do ln on both sides of the equations. And then I get x plus 1 times ln of 2 equal to 1 minus 2x times ln of 5. Right. And then I just distribute ln of 2 on the left-hand side, and on the right-hand side, I distribute ln of 5. I got x times ln of 2 plus ln of 2 equal to ln of 5 minus 2 times ln of 5. Sorry, 2x times ln of 5. The next step is to group anything related to x on one side of the equations and everything else on the other side. So I get x times ln of 2 plus 2x times ln of 5 equal to ln of 5 minus ln of 2. And on the left-hand side, I take x as the common factor. I get ln of 2 plus 2 times ln of 5 equal to ln of 5 minus ln of 2. And to get x by itself, I divided both sides for this number right here. And I get ln of 5 minus ln of 2 altogether divided by ln of 2 plus 2 times ln of 5. That's the answer. If you use the first approach, and you take log of base 2 on both sides of the equations, you should get something like this. So you get log of base 2 of 5 minus 1 divided by 1 plus log of base 2 times log of base 2 of 5. Is that what you get if you use the first approach? Yeah. You got the same thing? Yeah, okay. If you use the first approach, if you take log of base 2 of 5, if you take log of base 2 on both sides of the equation and you solve for x, this is what you should get. All right. And if you take ln on both sides of the equation, either one should work. Good. All right. So tomorrow we will continue with this lecture notes and we will get to logarithmic equations. Thank you for being here, everyone. Oh, one thing I want to mention, I sent out an email last week about the event on Thursday. So if you have time to go to attend the meeting, and if you attend the meeting, write down your name. I will give you 2 points for test 2.